All right, here we go. Welcome to video 2.3. We're going to learn today about how to calculate the displacement of an object that's accelerating, which is actually a little bit more complicated than you might think, and we will learn why. Here we go. So we've already learned how to calculate the displacement of an object that's traveling at a constant velocity, but what if the velocity is changing? So look at this, to answer this, we're going to look at two simple examples. So in example one, it says, suppose a car travels at 30 meters a second for 6 seconds. How far will the car travel in this time? So take a second, pause it, and see if you can figure this out. Okay, cool. So you're going to start by writing down what you know. Here's what we know. We know the velocity, we know that the velocity of the car is 30 meters a second. We know that the time is 6 seconds. And we're trying to find out how far the car will go. So we're looking for displacement. Now we need to establish what kind of velocity is this? Is this initial velocity, final velocity, or average velocity? Well, it doesn't say anything about the car speeding up or slowing down. The way it's worded, it sounds like for the entire 6 seconds, it's always going 30 meters a second. So it actually turns out that it's my initial velocity and my final velocity. And since the velocity is never changing, we can call it the average velocity. Okay, and think about what this number means. This number, as long as your velocity is constant, means every second the car goes 30 meters, right? So to find our displacement, here's an equation from the beginning of the year, or beginning of the class. To find our displacement, we just multiply the velocity by the time. So I'm going to say, oh, well, my car went 30 meters every second for 6 seconds. So that means that it went 180 meters, right? And that's it. Okay? So what it says under here is that this example is hopefully simple to solve. Like I say, hopefully you got this. Oops. Hopefully you got this as an answer. What makes it easy is the fact that the car is moving at a constant velocity. The car travels 30 meters every second. Okay? So what we're going to talk about today is what happens if the car's velocity is changing? What if it's not constant? All right, and so that brings us to example number 2. So at first glance, when you look at this, it says, suppose a car speeds up from rest to 30 meters a second in 6 seconds. How far will the car travel in this time? So at first glance, you look at it and you go, oh, well, let's see. I know that the velocity of the car is 30 meters a second and that the time is 6 seconds. And I'm looking to find out how far it goes. So at first glance, it seems to be the same problem. But there's a really, really important difference. And that important difference is this. In this problem, the car's velocity is not always 30. Okay? Because it says it goes from rest to 30 meters a second. So it's not going 30 meters a second until the end of the 6 seconds. So this actually is our final velocity, which then raises the question of, what's our initial velocity? Well, you got to watch. This is one of those situations where there's a hidden zero. Since it goes from rest, that means it was initially not moving. So our initial velocity is 0. Okay? So that's the problem we're dealing with here. We know our final velocity. Oops. We know our time. We know our initial velocity, and we're looking for the displacement. So we haven't learned the equation to do it yet. We could try to use this guy. We can try to use displacement equals average velocity times time, but we don't know the average velocity. We just know the final velocity and the initial velocity. So it turns out there's 2 ways to solve it. So here's option 1. The first way is to actually use this equation. Displacement is average velocity times time, but find the average velocity first. Okay? So in other words, it turns out, let me do this. Let's call this step 1. That's a T. So step 1 is find the average velocity. So in this problem, what happened was our initial velocity was 0. At the end of the 6 seconds, we reached a velocity of 30 meters per second. So it turns out that as long as your acceleration is constant, which in this class it always will be, so as long as your acceleration is constant, you can use this equation. So let's find our average velocity. So average velocity is VF plus VI over 2. You're just finding the average of 2 numbers. All right? Again, this only works if your acceleration is constant. So our final velocity is 30 meters a second. Initial velocity was 0 meters a second. Add them up, divide by 2, and you get an average velocity of 15 meters a second. So what this number is telling us is that while the car is driving, it averaged 15 meters each second. At the beginning, because it started out very slow, it probably went less than 15 meters every second. But by the end, it was probably going more than 30 meters each second because it was speeding up. But on average, it went 15 meters each second. Okay? So now that we know that, now we can do our step 2, which is to find the displacement. So displacement is average velocity times time. And we're going to say, oh, well, I averaged 15 meters each second for 6 seconds. So 15 times 6, grab your calculator, it turns out to be 90 meters. Okay, so that is one way to solve this problem. And I'll be honest with you, it's probably the easiest way to solve this problem. Okay, so I want to show you another way to do this also. Okay, this second option is going to seem more complicated. There will be situations where the second option is actually the easier one, and I'll tell you how to know which equation to use. But for now, I want to solve this problem 2 different ways and just show you that you get the same answer. Okay, so we're solving the same problem that we've just solved, where we know the following information. Our car starts at rest. It's going to speed up to 30 meters a second in 6 seconds, right? Okay, and we're going to try to use this equation. All right, it says displacement equals half of the acceleration multiplied by the time squared. Notice it's just the time that is getting squared. And then you add your initial velocity and multiplied by the time. If anybody's interested in where this equation comes from and you want to stick around either before or after school, I'm happy to show it to you, but my guess is that 90% of you don't care. But just know it comes from some algebra and using some other equations that we've already learned. Okay, so, but the problem is I can't use this equation right now because in order to find it, it requires me to know the acceleration. So once again, this is going to become a 2-step problem. All right, my step 1 is find the acceleration. So acceleration is Vf minus Vi over t. So final velocity is 30 meters a second. Initial velocity in this problem is 0 meters a second. Time is 6 seconds. Divide it all out, and you end up getting 5 meters per second squared. So every second, the car's velocity increases by 5 meters per second. All right, so now that we've done that, now we can find our displacement. So displacement is 1/2 a t squared plus, Vi times t, and plug in your numbers. So you get half of 5 meters per second squared, multiply it by your time, which is 6 seconds, squared, plus the initial velocity, which in this problem is actually 0, times 6 seconds, right? So grab your calculator, and you should literally do this. Grab your calculator and punch this all in, and you get, we should be happy to discover, 90 meters, right? We're happy because that's the answer we got last time we solved it. All right, so we've now solved this problem 2 different ways and gotten the same answer. And most of you right now are probably thinking, well, why would I ever use option 2? That equation is a mess, right? Look at this equation, right? This is like serious. This is high school math, right? Okay. So why would I do that? Well, let's try this again. Let's do another example. All right, it says let's use both options to solve this one. It says a motorcycle is driving at 24 meters a second and it slows down at 3 meters per second squared for 5 seconds. How far will it travel in this time? Okay, so let's start by writing down what we know. 24 meters a second, and actually at this point you should probably pause it and do this yourself. Write down what you know. Make sure you can do that. Okay, so it turns out the 24 meters a second is your initial velocity. The acceleration is 3 meters per second squared, and the time is 5 seconds. If you didn't, check your signs. Is the motorcycle speeding up or slowing down? slowing down, right? Which means that the velocity is going to decrease, so our acceleration is negative. So you might write that down. The acceleration is negative because the velocity is decreasing. If you don't know that, write it down. Okay, and we want to figure out how far it's going. Okay, so there's our given information. So using option 1, this is going to be a pain in the neck. Look, because remember, what I know is my initial velocity was 24. My final, my acceleration is -3 meters a second squared. My time is 5 seconds, and I'm looking for my displacement, right? So option 1 actually is not a good option here. Here's what we have to do. We've got to find our average velocity, right? But now we got to find our final velocity. So this actually becomes a 3-step problem. You're going to find your final velocity using this guy. So your final velocity is going to be right? You're starting out at 24 meters a second, decreasing by 3 every second for 5 seconds until you get to 9 meters per second. Now that I know that, I can find my average velocity. To get an average velocity of, what is that, 33 divided by 2 is 16.5 meters a second. And then finally, now I can find my displacement by multiplying 16.5 meters a second times 5 seconds. It gives us, what, 82.5, I think? Okay, so that works. It gives us an answer, but it was a pain. It was 3 steps, right? Okay, so it turns out for this one, option 2 is actually the easier one. So let's do it now. Here's what we know. We know our initial velocity was 24 meters a second. We know our acceleration is -3 meters a second squared. We know our time is 5 seconds. So, oh, we know everything. You just plug in your numbers. 1/2, the acceleration is -3 meters a second squared. Time is 5 seconds. Don't forget to square it. Initial velocity is 24 meters a second. Time is 5 seconds. Punch it all into your calculator and you get 82.5 meters. Okay, so to me that's easier because it's all one step, right? So last thing we need to talk about then is how do you know which one to use? Honestly, it sort of depends on what you're given. I have people who use this one all the time, and I've seen people use option 1 all the time. It's sort of whatever you're more comfortable with, but what I do is this. If I know both VF and VI, I use option 1. Okay, because if you know both VF and VI, it's pretty easy to find your average velocity, and once you know that, you can do this. Now, if you don't know VF and VI, you'll probably know your acceleration, and then I usually use this one. Okay, so this right here is a big reason why I keep saying write down what you know. If you take the time to write down what you know, it'll make it way easier to figure out which of these 2 equations to use. Okay, so I think we have one more slide. Oh no, forgot about this. You know what, we're running a little long here. I think I'm gonna not go through this right now. Maybe this will be something that's good to do in class. So I'm gonna start class with that. What I do want to do is show you this. We can work backwards. I'm going to do this in class too, actually, because we're running a little tight on time here. So we got to finish up these notes in class next time I see you. I've promised I'd keep the videos under 15 minutes, and we are quickly approaching 15 minutes. Really quick, pause the video right now and copy those equations down. Those are the equations that we've learned at this point in this class, and you will need them to continue and be successful. Have a good day.